2.7 Algebra 1. Let's do some square roots and dealing with some things with real numbers. We are on page 110 in your book. So let me get here, page 110. So let's check this out. We go square root. You can see there's a key concept box for square root. In it, square root sometimes is hard to explain. I guess the best way to explain it is let's do it backwards. We have squared numbers before, like 4 times 4 is 4 squared. Okay, and 4 squared is 16. So the square root, since see squared and square root, so the square root of 16 means which number do you square to get 16? And it has to be this, two numbers that are the same. So the square root of 16 then would be 4. The square root of 25 would be 5. The square root of 49 would be 7. And there are square roots of other numbers that aren't perfect. These numbers right here are called perfect square numbers because these answers come out perfect whole numbers. But if I said what's the square root of 21, then that one's going to come out not a perfect number. It's going to come out with some decimals in it. So let's take a look at Radicand. And the Radicand, square roots are used this symbol where I see where I have the square root of 16 like that. Okay, this right here is called the radical symbol. Okay, and this is called the radicand. It's the number underneath a square root symbol. Okay, perfect square, we talked about that. Like 49 is a perfect square number. 25 is a perfect square. That means another way to look at it is if you had 25 tiles, you could line them up in a perfect, you could set them up in a perfect square. 100 is a perfect square number. 144 is a perfect square number, and so on down the line there. An irrational number, we've talked about rational numbers, and if you remember the definition of a rational number was a number that could be written as a fraction. Well, guess what an irrational number is? A number that cannot as a fraction. And as you recall with decimal numbers, we can write decimal numbers in fractions when we know what the last place value is, like thousandths and billionths. That tells us what the bottom is. But if the number goes on forever, if it's a non-repeating decimal and it goes on forever, we cannot write it as a fraction. The biggest example of an irrational number is pi. Pi is a number that goes on forever. You would never be able to write it as a fraction. All right, and the last is real numbers, and I'm trying to find, I'm always not really sure what they want us to put for real. Oh, look on the top of page 112 in your book right now. It's got a really nice little, page 112, it's got a really nice little, almost like a Venn diagram right there. Real numbers are all the numbers, all rational and all irrationals, everything are all real numbers. So page 112, if you want to put that table in there, you guys can write that. Okay, so pause that so you can get it written, and then we'll be set. All right, so let's go to the first example. Example number 1, finding square roots. Evaluate the expression. I want the positive and negative square root of 36. So 36 is a perfect square number, so it would just be 6. And it'd be plus positive 6 or negative 6. The square root of 49, and since there isn't this little symbol in front of it, it just wants the one number, so it's 7. And if you look at this, how come 6, positive 6, if you think 6 times 6 makes 36, but also negative 6 times negative 6 makes 36. That's why there are 2 answers in that. This is the negative square root of 4. Well, the square root of 4 is 2. The negative is negative 2. The negative of the square root of 9 then is negative 3. The positive of the square root of 25 is 5, because 5 times 5 is 25. The positive and the negative of the square root of 64 is 8, so I put plus or minus 8. The negative of the square root of 81 is negative 9. Okay, those are perfect squares, so let's check this out. A folding table. is a square whose area is 945 square inches. Approximate the side length of the tabletop to the nearest inch. So they're telling us the tabletop is a square. Okay, they're telling us the area is 945. So we have to figure out what times what would get us that that number. So let's just start going through and looking at square numbers. I know that side times side, so I know that s squared has to equal 945. So I know it's got to be a pretty big number because I know the perfect squares we've been dealing with are pretty small. So let's look at 30 times 30 is 900. Okay, and then let's look at 40 times 40, which is 1600. So that tells me that the number's between 30 and 40, but I know that it's probably closer to 30 than it is 40. So let's try 31 times 31. And I don't know how the book does it. This is just the way I'm wanting to do it. 961. So I know then that it's between 30 and 31. Okay? So I think, let's see, 30 and 31, 945 is closer to 961. So it said approximate it, so we don't have to have the exact, so I say it's closer to 31, so we're going to say it's about 31 inches. And you say I just find in between two numbers, process of elimination. See how they did it. Kind of the same way. They just did 28 times 28, 29 times 29, 30 times 30, and they did the same thing we did. They found that it was closer to 30. It was between 30 and 31, and they know that 945 is closer to 961. So about 31 inches. Okay, so approximate the square root. So 32. So you think, what are the two perfect squares that 32 is between? Well, 5 times 5 is 25. 6 times 6 is 36. So I know the square root of 32 is between 5 and 6. Is it closer to 5 or is it closer to 6? So we're approximating. What is 32 closer to? 32 is closer to 36, so it's approximately 6. We know it's a little less than it, but we know it's approximately 6. 103, I know 10 times 10 is 100. I know 11 times 11 is 121. And 103 is closer to 10, so it's approximately 10. We know it's not exact, but it didn't ask us to find the exact, and it wanted it to the nearest integer. Those are integers, 6 and 10. They didn't want decimals there. The negative of the square root of 48, so 48 is, let's see, 6 times 6 is 36. 7 times 7 is 49. Obviously 48 is closer to 49. So it's approximately -7, and that's what my little squiggly equal sign means, approximate. Now it's getting bigger on us, isn't it? We go, well, I know 20 times 20 is 400, so now I got to do 19 times 19. 8, that'd be 17, placeholder 9, 1, 1, 6, carry the 1, 361. So it's not 20, so I got to do 18 times 18. 6, 8 goes into there. 4 times 324. So 18 times 18 is 350 is closer to 19 times 19, so it's approximately -19. So that's how you approximate your square roots. Okay, example 3, classifying numbers. Tell each of the numbers is a real number, a rational number, an irrational number, an integer, or a whole number. So, the square root of 24, in this case, the square root of 24, all numbers are real numbers. So we say yes, every one of them are real. Okay, so then we go, what's the next one? A rational number. Well, the square root, let's simplify. The square root of 10, or 100 is 10. The negative square root of 81 is negative 9, and the square root of 24, I believe, is going to, if you do it on your calculator, there's a little square, there's the radical symbol. I think it goes on forever on the decimals, so it's an irrational number. So it's rational, we would say no. 10 can be written as a fraction, yes, that's rational. Here, I think they have a table. Let's just look at the table. Irrational, the 24 is irrational, yes, and these aren't. It's not an integer, and this one is 10 and negative 9, and the only whole number is 10. Order the numbers from least to greatest. Well, when I'm putting numbers in order, I like to locate them on a number line. So it's a little tough here without, I would kind of, well, we'll just, so 4/3 is 1 1/3. There's 1, 2, 1 1/3 about right there. That's where 4/3 is. I'll put it in as the number. The negative of the square root of 5, the square root of 5, 2 times 2 is 4. 3 times 3 is 9. It's closer to 4, negative 4. So the square root of 5 is negative is going to be in there somewhere. The square root of 13, the negative square root of 5. The square root of 13, let's see, 4 times 4 is 16, 3 times 3 is 9. What is this? This is 1, 2, 3, 4. What did I say? 4 times 4 is 16. 3, so it's closer to 4 somewhere. It's up in here somewhere, square root of 13. And you could use your calculator to find the exact number. So a negative 2.5 is about right there. And the square root of 9 is 3, so it would be right there. So by placing these on a number line, we put them in order. That's first, that's next, 4/3, square root of 9, square root of 13. And I think it has them do the same. They're doing the same thing. And I kind of use logic from the last problems we just did to help with. Tell whether they're real. I'm just going to see if they put this in a table. Let's see. They did. Okay, so 20. It's not a perfect square. Most of the time your perfect square, your numbers that are not perfect squares are going to be irrational. They're all real. So not rational. Square root of 7 again, not a perfect square. So then those would all be yes, the rest would be no, and then opposite. See these two, how they're opposite of each other. Okay? The only integer is 0. Whole number, the only whole number is 0. Rewrite the given conditional statement in if-then form, then tell whether the statement is true or false. If it is false, give a counterexample. Given. No integers are irrational numbers. So, we're supposed to write an if-then statement for this. If, so let's come up with something. Their solution says, if a number is a fraction, then it is not. We're supposed to make a statement. Tell whether the statement is true or false. No, okay, the book says no this, I think this is wrong. Your book says no fractions. I'm looking at example 5 with you. So let's take a look at that. No fractions are irrational numbers. So if a number is a fraction, okay, that's the if part. Then we say then it is not irrational. Remember, irrational means it cannot be a fraction, and that is a true statement. Okay? So, the if part would be if a number is real, then, oops, then it is a rational number. Well, reals are all numbers, which include the rationals or irrationals, so that would be false, I believe. Because some real numbers are not rational. It's kind of crazy. Those are hard. Those are tough. We'll practice those a little. All right, rewrite it. Tell whether the statements are false. All square roots of perfect squares are rational numbers. So if the square root, it would be if a number is the square root of a perfect square, we would put the if part here. If a number is the square root of the perfect square, then all are rational numbers. That is true, because it would be a perfect square like 25. If all repeating decimal, how would we do that? If a number is a repeating decimal, then they are all irrational. That is false because 0.33 repeating numbers can be written as fractions. Irrational means they can't be written as fractions. Yeesh. No integers are irrational numbers. So if a number is an integer, then it is not an irrational number. Right, because it can be written as a fraction, and irrational numbers can't be written as fractions. Those are hard. You're going to have to ask me for help on those. Hey, give those a shot, and we'll see you next time.